she gets on.
Yes.
And then we took
Alright. Should we get started?
Let's
So we can wait.
give it a minute or so. They're just getting coffee.
Yeah. Spoilers.
Pointer works.
Let's work on that screen.
It's because in front of the TV, they have a mirror.
Mm-hmm.
Okay, so that is not the point to go to.
I like the setting, like in the conference room style for something like this, but on the screen, you can't use the pointer. Way too hot in there. Look who it is. Much bigger.
Yeah, the screens were a little
Yeah.
small yesterday.
I like conference rooms. And those chairs. We need those chairs all year. Last only 2.5 hours in this. My bag, everything is bigger.
I usually do.
All right, well, welcome back, everybody. I hope everybody had a good evening last night. We're going to do a half a day today. I think we finished around 11:30, 11. And so the kickoff is at noon over, you know, they coordinated that with us. So the kickoff is at noon, and we'll be heading, we have a reservation over at the, hey, you guys, we have a reservation over at the Federal Tap House. So, so come join us as long as you can stay. If you can stay. If not, you can move and stay virtually. So, unless you want to Michigan State. Okay, so anyway, our first presentation today is Peter Scarcella. So I'm going to turn this over to Peter.
Thank you, Dr. Spencer. Well, like Dr. Spencer said, my name is Peter Scarcella. I'm one of Dr. Spencer's PhD students. This work I'm going to be presenting today is based on my master's thesis. I'm just starting my PhD work, so looking for a new topic. And lots of the presenters from yesterday gave, you know, some considerations for topics to work on. I'll be presenting this presentation at the Spaceflight Mechanics meeting in Kissimmee. So any feedback that you guys can give me would be much appreciated. So the topic that I'll be discussing is a parametric trade study of multiple libration points in the restricted, circular restricted four-body problem. So a little background on what I was doing. So actually originally the mission was based on NASA's ARM mission, may it rest in peace. So I'm considering an asteroid flying information with a spacecraft in the Earth-Moon system about the libration EML1 point. So all figures that you'll be seeing in this presentation will be around that kind of orbit. So as you can see here from this simple diagram over here, this is just the dynamics of the problem. So you have the mass of the Earth and the asteroid. So the goals of this study is to look at short-term stability over roughly a period of 2 to 4 weeks. We'll be looking at impact avoidance and the overall stability of the spacecraft's orbit. And stability is defined here as it's the drifting of the spacecraft, whether it's closer to the asteroid or drifting further away. Also looking at the minimum optimal range between the spacecraft and asteroid, and any effects that the spacecraft has on trailing versus leading the asteroid. So the model that I'm using is the circular restricted 4-body problem. It's treated as basically two coupled restricted 3-body problem, which Davide kind of went over yesterday. So under this paradigm, the asteroid is basically treated as a additional gravitational perturbation. There are 12 equations of motion, 6 for the asteroid, 6 for the spacecraft, and looking at the dynamics of the circular 3-body problem. So M1 is the Earth, M2 the Sun, and M3 would be the asteroid in this case. And transitioning to the circular restricted 4-body problem. Like I said before, the asteroid is considered to be an additional gravitational perturbation. So for the circular 4-restricted body problem, you have the Earth, the Moon, and the spacecraft is M4 in this case, and the asteroid is M3. For the parameters of this study, I'm considering 2 halo orbits about the size of 2,000 kilometers and 5,000 kilometers. And the asteroid masses that I'm considering were based on kind of what the R mission was looking at a range from 25 to 200 metric tons. And all the figures that I'll be showing will be these ranges of masses. And then for proximity operations between the spacecraft and asteroid, I'm looking at a relatively close operational range of about 35 meters to something very far away, around, close to 900 meters. So looking at about a 500 meter separation, any further away from that the spacecraft initially starts from the asteroid, you don't really see much going on. The orbit is pretty stable, but at the same time, you're also kind of far away from the asteroid for studying or mining or anything. So the colors denote the mass of the asteroid. So the blue is 200 tons, black is 130, red 75, green is 25, and purple is just the baseline case where the spacecraft is just traveling alone. So the problem just reduces to a circular 3-body problem. So this figure shows the range from the spacecraft to the asteroid over a period of about 12 days, which is one orbital period. And this figure shows the range between the asteroid, the range difference. So between the baseline case and the cases with masses. So it's just simply taking of the spacecraft when there is a mass and subtracting it from the case when the spacecraft is traveling alone. So at this 500 meter range, the spacecraft doesn't really differ from its trajectory when it's just traveling by itself. At most, for like the 200-ton case, it's only about a 10-meter difference. And so the effects of the spacecraft, or the asteroid on the spacecraft at this range, are fairly negligible. And over a one period orbit, the orbit is very stable.
Yeah. On the range difference, you cannot. I know how you explain it, but you cannot portray negative numbers there.
Mm-hmm.
It's just, if you want to call it, if you do it vector in evolving directions,
Mm-hmm.
you can put a negative. You cannot do that.
Okay, thank you. So looking at the relative position between the spacecraft and the asteroid, again, over just one orbital period, you can see that the orbit looks, and for the purposes of for this, the short duration of the mission, this is good. You don't need a lot of delta V to. You don't really need much in the way of delta V to, maintain the orbit, and the orbit's just very stable. And for the 300-meter initial separation, you begin to see some effects of the asteroid's gravitational source. Towards the very end of the mission duration, about over the last couple days, you begin to see the spacecraft starting to drift away from the asteroid. And again, looking at range difference, you begin to see that the range between the spacecraft and asteroid has roughly doubled, moving about a couple hundred meters closer to the asteroid, which is what you would expect to have more perturbations the closer you get. And again, just looking at the relative position between the spacecraft and asteroid compared to this relative position, you begin to see the effects of the proximity that between the spacecraft and the asteroid. And as you get closer, your delta V requirements increase. So jumping forward, going right next to the asteroid, about 35-meter distance, this is a close-up plot of the range between the spacecraft and asteroid. And these dashed lines at the bottom represent the radius of the asteroid. So if the range crosses any of the dashed lines, it means there's an impact. And if the line gets very close to the dashed line, then it's considered to be a near miss. And basically at that point, the spacecraft just veers off into space, like the trajectory goes way off. And looking at two orbital periods, again, just looking, if you remember from before, for about 500, for the 500-meter initial separation, it was very stable over just one orbital period. But as you go for another period, so you're going for about nearly a month mission duration, during the second period, the spacecraft starts to drift away from the asteroid. And as you can see here, For the 200-ton mass, you have about a range of nearly 2,200 meters, which is very unstable. So if you want to stay in orbit for 2 orbital periods, you're going to need to expend a lot of delta V. Now, before I was just looking at the large orbits. For a small halo orbit, just considering the baseline case where just the spacecraft is traveling alone, there is, I don't know if you can really tell from here, but there's a slight discontinuity there. And this is what touches upon what Davide was saying yesterday, how small halo orbits around libration points are inherently unstable. And so you really don't want to use a small halo orbit in the libration point orbits because they're just too unstable. And I eliminated any sources of numerical error looking at the dynamics of this, just to make sure that discontinuity was not a source of error, or it was just the dynamics at play. And again, just for as you increase the mass of the asteroid, just the discontinuity even at an 800-meter range becomes way unstable. So only larger halo orbits can be considered. And again, just looking at 2 orbital periods, the spacecraft just completely changes inclination and exits the orbital plane, and never to return again. So like I just touched upon before, I did several numerical experiments to determine the validity of the dynamics that I was seeing. So I used a variety of tolerances. The tolerance ranged from about 1 to the minus, or 10 to the minus 13 to about 1 to the 10 to the minus 2. And for most of that range, the dynamics stayed the same. And at the larger end of the spectrum, that's when you started seeing a lot of variation. So you can conclude from that the dynamics are good, and the numerical error is very small. I used a variety of numerical solvers: a Runcutter, Dorman-Prince method, Runcutter, Bogacki-Champagne method, and Adam-Bashforth Moulton method. And like I said, the analysis shows that the dynamics are what are at play here and not numerical error. Some conclusions that we can extrapolate. Like I said before, small orbits are completely unviable, and impacts only occur when the orbit is inherently unstable. So if you have a stable orbit, there are no chances of impacts occurring. So basically, an impact will only occur unless you want an impact to occur. Stable orbits are within the 300 to 500 meter range. And looking at trailing versus leading spacecraft, it has no effect on the dynamics of the situation. The numerical study, like I just said, shows that the dynamics are producing all the results, and error is not really having much an effect in what you're seeing. The aforementioned qualities give mission planners a lot of flexibility in designing orbits for potential missions, and using the orbit states from the spacecraft, you can determine characteristics about the asteroid. Any questions?
I may have missed it because I walked in a few slides late, but what did you believe, what were some of your conclusions on some of the integrator testing that you did, like qualitatively? What did you notice about some of them? Because you made lists of like 4 of them.
Yeah.
I'm kind of interested in what you saw.
So for the Runcuta dormant prints, I found that as you increase the tolerances for that, the results were held up better for higher higher tolerances than the other methods. Actually, they're kind of actually listed in order of how effective they were versus the tolerances. So the Adams-Bashforth method actually didn't perform as well as the other 2. It started having wildly crazy results, probably around the order of 10 to the minus like 4, whereas the others were more around like 10 to the minus 2, where you started seeing a lot of variation.
Sorry, how we have today?
I guess the meeting's over.
So I just, we just could never meet them.
About 70. Yeah. Said okay. Did you say it started? Fix it in a minute.
Yeah. Whoops. Yeah.
Peter, I had one question. Can you go back to a couple graphs ago? You showed something with a radius and an asteroid.
This?
Yeah. Did the colors have anything to do, like, is the radius being 200, is that like 200 meters?
Okay, so the numbers over here denote the mass of the asteroid. So the actual radius is just simply
Whatever
the height, yeah, whatever value that is. So I think for like the radius like ranges from maybe
You assume it was just a sphere.
yeah, just assuming a spherical.
As you increase the mass, the radius got bigger.
And I assumed the density of the asteroid was similar to what the R mission was looking at. Like they were looking at various or a certain class of like asteroids. So I based the asteroid specifications on what they were looking at.
So essentially, if the red curve crosses the blue dashed line, that doesn't mean anything to you.
yeah.
It's just the red dashed line that you're looking at.
Yeah, so the colors have to match. So if it crosses, if the red line crosses the red, if the red line crosses the red dashed line, that means there's an impact. However, if it crosses the red crosses the blue dashed line, no impact.
So going back to the integrator question, were these all of the same order? Is it like 4th order, 4th order, 5th order?
Oh, so this was a 4th, 5th order method, and this was a 2nd, 3rd order. And this method was a 4th order.
You consider trying a higher order, like cut on something like an 8th order or the other, which is used for a lot of mission analysis.
Okay, I can keep that in mind.
Even the
yeah,
variational integrator. Variational integrator.
a variational integrator?
Yeah, they try to, generally they use a lot in the long-term propagations because they try to, step size is decided based upon the conservation of energy or the momentum. So that might be the. Another question, is your sphere is solid or it's hollow?
Is what?
The asteroid, we said that you're modeling it as a sphere of a radius. Is it a hollow or a solid?
It's solid.
Solid?
Yeah.
Okay.
Solid with constant density based on densities on rock that's
Sure.
the easiest way to see. And it's also cervical too, so.
Yeah.
Yeah.
Any other questions? Next, the
We're trying to do that multiple times if people don't call in.
I know. No one likes us. Saturday morning, all better things to do.
Well, you can call in with mute from your computer just to keep it from breaking.
I could use a phone actually probably the best bet. His computer has to install the software. That's a good idea.
Should I wait until 9?
I mean, if someone really wants to be calling in, they should call in a couple minutes early anyway.
Good morning, gentlemen. Ooh.
There we go.
Right on time.
Okay, I'll just start early. Thank you for having me. It's really nice to come back here to Penn State. So I had a talk that I created as sort of a caution. It's sort of I tried to come up with potential ideas for people who are doing some soul searching on their research still. You can take from this what you like, but I get a chance to do a lot of journal reviews and talk to a lot of people at conferences and ingest a lot of things. And in so doing, I feel like I build up a lot of ideas for research problems that I'll never have the time to work at all. And so I didn't really build a big list of things, but I touched on things that it seems like there's some potential. So I'll get into that in a little bit, but that's the basic idea of how I tailored the slides. And then I took some methods that I favor for low thrust trajectory optimization. Not saying they're the best or the worst. Well, I think that they're good. And then I showed how you can actually apply them to the design of an upcoming NASA flight mission. So just putting it all together. Wow, that's great. Okay, let me stand here. Okay. So I also gave a little bit of about me section just because I passed through Penn State, and so it's an about me, basics of low thrust, so we're on the same page. I think I can go fast through that because based on the presentations I saw, everybody kind of knows what's going on. And then some of the solution methods that I prefer that work out well for me, and then a mission example. So for me, I came right here through Penn State in '03. Both Chris Scott and I were classmates here at Penn State, so it was really weird that we ended up becoming office mates at the same place eventually. But really, I owe everything to Dr. Spencer and Elton. I mean, it was their class that really resonated with me, and that's why I'm here still. So I mean, those were some of the best classes I ever took, and I still remember them. And I actually teach classes at Hopkins now, and kind of use some of the ideas from Spencer's class, where I don't know if you still do this, but at one point in our class, you were doing like a mission of the week and kind of talking about that with the class. So I took that theme, and that really seemed to resonate well with the students at Hopkins, and they like it a lot. So it's kind of a 450 style class at Hopkins, so that's a lot of fun. And then I went off to Purdue under Kathy Howell, did a MS and a PhD. That's where I got into dynamical systems theory and low thrust and trajectory optimization within that group. So she's got more of a dynamical systems tilt, but I was really interested in trajectory optimization, so I kind of combined them into a dissertation. And then from that, I did fellowships with NASA, and that's how I got into all the interplanetary mission stuff, and found out about APL and all the great stuff they were doing there, Jim with Messenger, and which I think most of us saw yesterday, and so just knew they were doing really cool work, so I'm lucky enough to be working there now. Okay, so electric propulsion. Here's a picture of the NASA Evolutionary Xenon thruster, which has not flown yet, but has, I believe, over 60,000 hours of ground testing time, and it will fly soon, hopefully. But that's what it looks like. And so just to get us on the same page, which I think we are, electric propulsion is producing, just to think about it, it's producing about 4 sheets of paper worth of thrust. At least this one is. That's a 7 kilowatt thruster. So you take, without going through all the physics of how it works, you take 7 kilowatts of power, which is a massive, massive amount of power, and that's the payoff that you're getting. Now you're getting specific impulse out of it, so it's highly efficient, but you are cashing in solar array size to get that. So it might come for free.
Just one thing, I appreciate you putting that force level up there. They just for a reference, yesterday in the presentation was talking about messenger, the helium gas pressure.
Oh yeah, I saw that. What was that?
I didn't say it out loud.
I
but
saw
it
the text. Yeah.
It started out at 1.25 newtons and went down to 0.25 right before.
Yeah, and that's just pressure.
Yeah, that's just
pressure.
pressure. So
Yeah.
that's on that order of magnitude there.
Yeah. So the trajectory is significant.
Yeah, it's like a little gas leak.
Yeah. Yeah. The people that do that are propulsion, propulsion researchers jokingly call this mouse fart technology. So, yeah, you can see why. So it, obviously it changes what the trajectories look like, and that's why we're getting into all this. And you can see the orders of magnitude of difference with chemical propulsion. But again, payoffs in ISP, so you can run the engines forever, about 10 times as efficient. Where does that pay off? Just looking at simple LEO to GEO examples, here's where you are in the percentage of payoff of useful mass after you execute your delta V. You're kind of in this region. So about 50%. The delta V is around I believe around 2.5 kilometers per second that it takes to go from GEO and do the home in transfer. Doing that same transfer, the delta V requirements go up a little bit because it's finite burns, so the burns are always in the optimal places. But it pushes you over to the right because your ISP is so high. So you're up here in Smart 1 went out to the moon and did about, I think, about 3 kilometers per second, and that had a thruster that was on the order of 3,000 seconds of ISP. So even with that higher delta V, pushes you all the way over to here, about 85% of useful mass. Same thing, Dawn, which is it Dawn? I can't remember if Dawn's done. I know it's close. Yeah, it's near the end. Oh yeah, it's near the end of its life. Yeah, but yeah, right. So Dawn has done an incredible amount of delta V. So electric propulsion, even though it's more complex, it opens up a gateway to higher delta V missions. So it pushes you up here. Otherwise, you got to get real clever, like Messenger did, doing all your delta V with trajectory gymnastics with gravity assists, which also costs time. So that's a little bit more timing based. This you're just doing it with your thruster and just brute forcing your way there. So either way, electric propulsion does have a lot of potential for missions that really need high delta V. Usually that means asteroid rendezvous type missions. Those are especially hard. Inner solar system is challenging too, as you saw with Messenger. So the next Mercury mission will be doing that with low thrust for that reason. So when I first started grad school, I thought that low thrust was this really new technology. It turns out it's been around since the 60s, and people are already using it a lot for station keeping. So this is a really cool picture that Aerojet shows to people to show that there's actually a lot more satellites out there than you think that are using electric propulsion. Now, the difference is that most of them, until recently, haven't used it as a primary source of propulsion. So the north, south, east, west station keeping that Vallado was talking about yesterday, all of that was being done by electric propulsion, just so you can stay up there longer. Now, the difference is that it took people a while to sort of embrace this as a technology they want to use for primary propulsion because of the time penalty to spiral out into GEO. But again, seeing that useful mass plot and knowing they can put stuff that's a lot bigger out there, it's made people rethink using it as primary propulsion. And then again, the deep space missions have already used it for these high delta V missions. Here's Dawn and Hayabusa out here. So I think we're kind of at a tipping point for solar electric propulsion where it's starting to get used as primary propulsion. And there's also buses that Boeing and Lockheed now offer that are being used to basically fly spacecraft. And that's really, so they're now coming off the shelf as opposed to being these like one-off specialty builds. And that's really what's causing some of the tipping point. So in terms of designing the trajectories, the research has been around for a while. There's no perfect solution to how to do these things, and it's really dynamically dependent with the regimes that you're attacking. I gotta check my time just so I don't take forever here. So you have to do this balance of spacecraft power, number of thrusters, propellant, design the optimal spacecraft. Usually you frame all of this in the context of an optimal control problem. That was kind of weird to me when I first learned it, because when I joined Kathy Howell's group, I was doing this libration point orbit targeting stuff, and I was thinking, why don't you just target, write a differential corrector and do it. Then I realized even differential corrections, that minimum norm solution is itself an optimization algorithm of the direction that you should be going. But really, it's because delta V is not the right thing to handle anymore. You want to carry usually a useful performance index for solar electric propulsion. Usually that's time or final mass. And so you take that and you formulate an optimal control problem, and you're basically just trying to find, as everybody here knows, I didn't go through fast this, trying to find a direction, magnitude, and control history that gets you from point A to point B. Sounds pretty easy. I think we all know that that can be a pretty challenging problem. Dr. Melton showed this yesterday, and a few other guys showed this. So we all know that there's these two methods that you can use to solve the optimal control problem. I've done both. I've done indirect and direct methods. I have a lot of love for the indirect method because that's the one that I started out using. Somebody said that they thought the indirect method was slower yesterday. I'd have to see what you're doing. I actually disagree with that completely. I think it's the one that's really fast. If your guesses are close. The problem with the indirect method isn't necessarily that it's a bad method. It's that numerically the solvers have struggles with the way that the control switching structure goes. Gradient-based methods don't like when there's these discrete switches that bang on and off. And so really it's the solver that's struggling with how to solve it. It's not that the method, the indirect method itself is bad. It's that the technology that we're using to find the solution struggles with the inherent underlying mechanics of the problem solution method. So that's kind of why people have gone to direct methods. With direct methods, you can get away often from some of this nightmare of the switching structure, and you can expand your convergence basin. What that means is that you usually grow your problem to something that's a lot bigger, but it's more manageable in terms of robustness. So you trade off robustness for speed. And in low thrust, people had slides that, we were all speaking the same language. So chemical usually have like a medium fidelity Lambert type thing, and or your three body type problems. And then you have high fidelity where you're transitioning into the ephemeris. Low thrust, there's kind of three different levels of fidelity that people use. Low fidelity is when you have these analytical representations of the trajectory. You say, I have a shape, for example, a logarithmic spiral, and I want to find the shape that actually is a solution to the underlying physics of a low thrust transfer. Problem with that is as you start to model hardware with power and stepping and all of that, by the time you get from here all the way down to here, sometimes the underlying assumptions of those solutions can break apart, but they're really nice because they let you just blow away the solution space with hypothetical options. There's actually a lot of work that needs to be done here still. If you're more into analytical type work and the math and the physics and coming up with ways to exploit that, this is kind of where you want to focus. There's a lot of potential in this area still, and a lot of people still working on it because again, the solutions tend to die as you get to high fidelity. That's really the problem that people have with it. So where most people spend their time with low thrust, you'll see is in the medium fidelity regime. So you've heard of the solver Malto and things like that, and EMTG that they use over at Goddard. Those are medium fidelity solvers because you can get the hardware modeling the way you want. The problem is it's already a numerical method. So you can do fast integration because you make assumptions about the dynamics that simplify them, but you make the hardware accurate. So it's numerical, it's pretty fast. It's not as fast as one of these, but with enough computing, you can still beat the problem to death and usually have a fairly easy time getting to this step. So in your GTOC style problems where you have all these crazy low thrust transfers, most people are in this regime right here, getting themselves here. Sometimes people can start here and get all the way down to here, but if you can do this well, this is where the potential is. But these methods are very mature right now, so people tend to like them. And then high fidelity is bare too. It needs a lot of work in terms of R&D. So there's different tools for planetocentric and heliocentric because of the underlying nature of how the trajectories behave. So let's talk a little bit about that. I'll just touch on it right now. So basically, planetocentric transfers with this, very low thrust result in many, many revolutions, hundreds, thousands of revolutions, and so that's challenging. Heliocentric, you're dealing with gravity assist, so things change there as well. Different assumptions needed for different regimes. Very seldom that you'll find a tool that's built to handle both of those design regimes. You'll find tools that can do it in high fidelity, but if you don't know what your solution looks like already, you're basically dead in the water. So I came up with a couple slides that I called just methods that work for me, because I've tried a lot of different methods, and I'm just telling you the ones that I prefer that seem to have a really nice payoff for challenging problems. So let's talk about the planetocentric problem where you have these spiral trajectories. I believe the creator of the equinoctial elements is actually on the phone, so this is pretty cool. So yeah, I really like to use the equinoctial equations of motion. These are just the coordinates right here that I'm showing, but they're very nice because they eliminate singularities, and if you have transfer trajectories that build up and flip over to hyperbolic, it's nice for that too. So the challenge for these many revolution planetocentric problems is that you have a fast variable that's evolving over time, right? So you're going to run your thruster, row your trajectory into this long duration spiral, something, I'll go to the next slide to show you what I mean, something like that. So, and you can imagine if you're trying to come up with this steering history, you're trying to solve a steering problem, point the thruster in the right direction and optimize that over hundreds of days, you're talking about thousands to hundreds of thousands of decision variables all at once. So what can you do to simplify that problem? One answer is to basically average out the fast variable. And so when you do that, you take some integrals, get rid of the fast variable, and you make some assumptions on what you're doing on a per revolution basis, and you basically optimize that problem. From that, you can take a problem that would basically take you, at least with today's technology, days to solve on a computer for a single transfer, and you can look at the averaging problem and solve that within, when we look at these, we solve them in like 15 seconds. So significant payoff in compute time, and you can actually fly out those control laws and more or less get what you would expect. So you can even use those as like an in-flight guidance if you really wanted to. So again, huge payoff on eliminating the fast variable. There are software packages out there that have done this, that NASA has built before, but it's kind of getting reopened again because of these transfers becoming of interest. So yeah, you can use the control history and high fidelity solutions. I think that's kind of cool. A lot of times you think, oh, I averaged out the fast variable. It's such a bad assumption, it's over. But if you fly it out and look at what your transfer does, it actually kind of looks like this. This blue is eclipsing, by the way, so you can bake that into the problem too. Cons, you don't know where your spacecraft is in its orbit, and it only really applies to dynamical regimes where the average behavior holds. For example, if you're getting out towards the moon and you can't really average what the moon is doing if it's something that's happening like on a one-off situation and it's not an average behavior. That's something that you can't really, you can model that early in the orbit, but as your spiral tends to grow and you're getting close to something like escape, averaging is not really the right choice for you. Okay, so that really works well for me. This is a hard problem that I struggled with for a long time. Maybe other people don't, but this really, really helps for the many revolution problem. And you can use the resulting guess in a higher fidelity method to resolve the problem. So to get started, this is really nice. And this is how institutions like the Aerospace Corporation, who fly many spacecraft for industrial customers, this is how they start too. Okay, so interplanetary. Again, I want to talk a little bit why this method works pretty well. Let me see where I am on time again. Okay, so a lot of different ways you can tackle the multi-gravity assist interplanetary problem. These problems come up in GTOC all of the time. You can solve this with a classical indirect method, and there are software packages out there that do that. Main EP used to be called Hilltop is one that does that, so that you can do it. I tend to prefer the Sims-Flanagan transcription because it has a significantly wider convergence basin than indirect methods. Again, this gets into the mechanics of how things work. So What the Sims-Flanagan transcription does is it does this small impulsive burn thing where you just stack enough of delta V's up, and you basically do what would be a chemical transfer discretized into little delta V's. The flyby you model as a patch conic flyby, and then you forward and backward integrate and just drive the solution, the discontinuities down to 0 with an NLP solver. So like that. Let's see here. So those are your match points. Okay. So if you do this with an indirect method, the problem is that you get, again, you get these problems in the underlying structure of your Jacobian, of your derivatives with the switching function. So it's not that the indirect method is bad, it kind of just struggles under the hood with the way that you currently need to solve the problem. The nice thing with this method is that since you've discretized it up, you're actually jumping through the discontinuity with the discretization. So it'll still exist, right? But you're never exactly on it with one of these points. So what you'll see with solutions that come out of a Sims-Flanagan solver, you can see it right here. Here's one. The discontinuity sort of just gradually disappears. And so even though that's a concession that you make with accuracy, if you were to fly this, you would know a discontinuity would be there. That little idiosyncrasy of how the formulation works is really what's kind of enabling this whole robustness thing to work. And so it's worthwhile to think about that, because everybody says direct method's good, indirect method's bad. Like that's really that's why it's better. That's what's going on under the hood. Need to think about. So you don't have to guess the engine on-off times. If you do the indirect method, a lot of the time you have to pre-guess how you think the switching structure will work too. That can become a challenge. There are ways around that, but again, you basically have to build in the switching structure of the engine into your problem formulation. When am I on and when am I off? And that becomes a challenge. The whole NLP solver is sort of taking care of it for you. That's really nice. I will say that these methods in particular, the Sims-Flanagan transcription, are analytical partial derivatives are absolutely necessary. So if you do this, basically your derivatives underlying in your NLP problem, you get these big Jacobians. If you do that numerically, you're talking about reintegrating the trajectory hundreds and hundreds of times just to step forward once. If you do analytical partial derivatives, you can calculate all of that on the fly with one propagation of the trajectory and then iterate forward. So it's a massive payoff. It takes time. When I programmed one of these methods, I think that was 3 months of my job, was just programming derivatives, but the payoff was there at the end. One of my grad school colleagues once told me that character, I don't know if that's true, I just lost life. And Chris told me that was my whole career was taking derivatives, so I don't know if I really like that. But let me tell you, when you get those derivatives in there and they work, it's a great feeling. It's like a nice glass of wine or something. Okay, so here are some solutions. You can get some really challenging solutions really fast with Sims-Flanagan. Here's a reconstruction of the dawn trajectory. So you can have all the accurate N-star engine characteristics, the on-off times, the hardware models, the force coast, gravity assist. It's not too hard to do when you use the SFT. So it's a really nice method that I like a lot. But again, you can do this with the indirect method too. Here's another challenging trajectory. This one was called Mirror. It's an example that's in the literature, and you can reproduce this too. So these are things that you can program your own versions of and get your hands dirty, and it's a lot of fun. Okay, but you make assumptions about the physics that basically aren't true, so it doesn't really hold for high fidelity, but it's a great way to get an initial guess for higher fidelity. Let's see, I'm doing 10 minutes. Okay. So when I was a PhD student, I spent a lot of time on collocation methods. I think these methods work really well for high fidelity when you don't necessarily have the most amazing guess for your path. Actually, it works pretty well when you have a good guess for your path too. Saw people who talked about these already. Again, I'm just going to give like a brush stroke of how they work rather than going into all the math. But basically what you're doing is representing your entire path with piecewise polynomials, which, by the way, is what numerical integrators are more or less doing anyway, but you're kind of doing it inversely. So you're using piecewise polynomials, carrying those around in an NLP problem, and rather than explicitly propagating forward with a propagator, what you're doing is baking that into your NLP problem and inversely solving the the conditions that must exist for that that path to actually match one that would obey the laws of physics. So you're kind of doing something like this, where you have this green path, and if you imagine that's truth, and you have this polynomial path, and you imagine that's what you're guessing in your NLP solver, what you're really trying to do under the hood is match this red path to this green path, and when you do that, you have a feasible answer. And then you have optimization as well. So problem just becomes dimension. So if you have a really complicated transfer, imagine this is like one segment for 10 degrees of true anomaly in your low thrust spiral out, and you do 1,000 revs. Think about how many decision variables that is that you have. So you can't just fire this off and do a broad trait study of all low thrust spirals that could ever exist. It's just not going to happen. So you want to usually use these collocation type methods, at least in this context, as a final step to push your final solution, because you're just talking about carrying around a lot of decision variables. But you can get really cool solutions. This was just a movie of something that I did in grad school, where we were trying to use a low thrust engine to stay below the lunar south pole as just like a mission concept study. This was all done with collocation. You can see it's a really complicated path, and the optimization was trying to drive the spacecraft so that it never comes up over the moon. It turns out, if you make some modest assumptions, you can at least show that it's physically possible to do. So you'll see there, it's hard to see, but the spacecraft is actually never coming above the pole. So it's on this very non-Keplerian trajectory. It's a rotating frame. That's why it looks a little bit weird. It looks a little bit more standard in a non-rotating frame. But yeah, so these are coasts. So it was trying to optimize all these coast arcs to maximize its mass. But we basically had to solve this with collocation. So this was about 100,000 NLP variables, but you can do it. So just trying to drive home the point that this is a good method for higher fidelity type problems. Okay, methods that work that I haven't used. So I'm actually going to talk about something that I haven't done before, but I think it's worth mentioning. Sorry, checking. Okay. High fidelity method that works for kind of any regime, but it's super numerically intensive. I've been wanting to get into it for a while. So people who are doing soul searching on low thrust, I highly recommend this area if you're into like high fidelity low thrust optimization. So this is kind of a shift that's happening in the field for research. You'll start to see a patchwork, presentations here and there. It's really challenging, but basically it's the differential dynamic programming approach. The idea has existed for a while, but computing speed has kind of lagged the ability to implement it. That is no longer true. So the way that this works, again, I'll try to just explain it with a broad brushstroke, is that you do an integration forward with an initial guess, and then you do this backward sweep in chunks, and you do this quadratic approximation of the trajectory. From that, you build up guidance laws so that next time you integrate forward, your trajectory is a better guess of the optimal one. And so you do this forward and backward sweep over and over again to try to get to the right answer. In 5 seconds, that's basically how it works. So this is partially what's going on in JPL's high fidelity software. It's called Mystic, that they use to fly Dawn. They use this general idea. And there are papers out there that you can read by researchers that have come since, that have basically open sourced this knowledge to the community. Problem is, there's first and second order partial derivatives that are needed to do the entire thing. So if you're afraid of partial derivatives, like, don't do this. but if it takes a lot of overhead work to get going. But once you get it, there's a lot of R&D type problems that exist. And again, if you peruse recent conferences and look for HDDP methods, usually by Ryan Russell's group, you can kind of see where they're going and some of the problems that they're having. And there's plenty of things that need to be tackled in this area. But this has tremendous robustness when it's working. More than the collocation methods, I've seen problems with very poor guesses converge. So it may have the widest convergence basin when properly implemented, at least from what I've seen. So I have no time left, but let me just talk about putting it all together in 5 minutes. So I'm working on a mission at APL. It's called DART. It's the Double Asteroid Redirect Test. It's a planetary defense mission. It's Class D, which means it doesn't have as much paperwork and review stuff, or a little bit more cowboy style. I think NASA would hate if you said that out loud outside this room. But it means that we work a lot faster, and it's supposed to result in lower cost. We'll see if that's actually true. And so the way this works is DART is a small vehicle that didn't really have a good launch vehicle. It's a small spacecraft that didn't have a good launch vehicle fit. So we were going to have to buy this, $120 million launch vehicle for this 200-kilogram spacecraft. NASA wasn't very happy about that, so we came up with this idea to launch it into GTO with other satellites, or to hitch on to another satellite that's launching. It's kind of TBD. So there are many satellites that go to GEO. This would be one that would hitch on, and then from GEO spiral out. So that drives the launch cost down, pushes you to electric propulsion, because if you're in GTO, there's a tremendous amount of delta V that you have to use to push yourself away from the Earth. And so this is a picture of the way the DART's working. It basically fires up its engine, does a long duration spiral for 6 to 9 months, gets out of the Earth and escapes, gets into interplanetary space, does a rehearsal flyby of a potentially hazardous asteroid that happens to be fortuitously en route to the final destination, which is this binary object. It's a potentially hazardous asteroid that has a very nice close approach with the Earth in 2022. And so it's actually going to impact the secondary, use that deflection of the secondary with respect to the primary, because it's easier to measure and test for planetary deflection, of asteroid deflection. And so all of this is built on this big low thrust transfer that you see here. And this is kind of a cool movie. I'll show this too. The very end doesn't use any low thrust. They're actually using terminal guidance that's based on missile defense to sort of fine tune everything on the way in. I'm not involved with that, but that's what the end game uses. So kind of neat to see. So the preliminary and detailed design are using some of these methods that I just talked about. Ignoring all this stuff, the initial trade study step, we're using orbital averaging and Sims-Flanagan transcription. So medium fidelity and averaging out the fast variable. The reason we do that is we need to know all sorts of information about configuration, launch date. You can't just wait a month to get one solution and tell other engineers that you understand the design space. So we back up the fidelity, we explore all different configurations, and then we use that to settle on a design that we like. And then from there, we move over and we put all that together into a high fidelity solution. Using both of these two approaches, the Sims-Flanagan step and the orbital averaging, we basically patch it all into a big guess for collocation, and then we solve it with collocation. Here's just some pictures of what it looks like. So yeah, it has a really complicated spiral out where we have to plan for eclipses, tracking arcs, all of that stuff, and bake it into an optimal trajectory. So these are just some pictures of what it looks like. So you have this spiral. We actually intentionally avoid the moon. So we avoid the moon. We have to escape the Earth. Once we're escaped, we're in interplanetary space. That's out here. And so yeah, your energy with respect to the Earth in a two-body sense is 0. This is a rotating frame. You do a flyby, this rehearsal flyby right here, and then you fire up your thruster again and get yourself to terminal impact. So somewhere around here, right here, you have this terminal guidance that comes on, and that's all chemical, and that's using that sort of missile defense type technology to get you from here to once you can actually see what the binary looks like more accurately, you can correct everything at the last second and get it there. So yeah, in summary, I think low thrust requires these different approaches. It depends on what regime you're in. Are you planetocentric? Are you heliocentric? Are you doing trade studies? Do you need a final solution that you're just trying to fly out for a mission? So those questions lead you to the answer of how you should be. So those are things you need to think about. Let's see. I don't know why I said existing state of the art. Oh, facilitates. I thought I said facilities. So yeah, the current state of the art is pretty nice right now. Like you can do trade studies and you can design complex missions, but there's a lot of improvements that can be made. I think I have some of that in backups. Yeah, backup slides. So these were just some ideas I was coming up with. I think the community needs much more accurate low fidelity methods because most people tend to ignore these. They exist, but they're not good enough to help you get to high fidelity. Again, these are sort of more mathematically intense and analytical, but that's what you're interested in. I would suggest going down that route. You guys are already well aware of this one. Global optimization isn't going away, but this stuff would help you with global optimization, but it needs research. So yeah, GTOC's not going away. I think more advances to the HDDP approach that I touched on. It's an emerging method, and in talking to Ryan Russell down in Texas, he's kind of talked about how he believes it's like a low, assigning technology readiness levels to things. He thinks it's a low TRL method that has potential for, very high payoff, but lots of cool research to do here. Some people brought this up. All of these methods, with the exception of HDDP, all of these optimization methods are tied to NLP solvers. So, you're only as good as your underlying solver, once you tune everything just right. So lots of research to be done in improving NLP methods. And many of these approaches, I didn't touch on this at all, have these parallelizable structures that can be completely exploited, and it's not really being done enough to make them better. So I think more work to be done there as well. So that was my backup slide. I think I'm done, so I'm happy to answer questions.
One of the questions you mentioned before is that when using the variation calculus, the integrated will broke when reach the switch point.
Yeah.
I encountered this phenomenon a lot. Very frequently. Is there a way to?
Yeah. So what you do is you can put usually. So if you're going to solve the indirect method and use that approach, what you want to do is add stopping conditions to your integrator so that it stops at a switch, and then you record the state variables, and then you restart it again until you get to the next switch. And so it's like a chained integrator. Yeah, yeah, and then you make that into a subroutine, and you just call that like low thrust propagator. But it always switches anytime the engine switches. What you can't do is propagate through a switch. You can't just put the indirect state co-state low thrust parameterization into an integration without doing that stopping. But even my larger point was that even with that, there's a high sensitivity in your partial derivatives that's introduced into the problem. But yeah, so step one is do that chained integrator, go right to the stopping condition, and then pick it up again. And you basically have to do that to get the sensitivity matrices and everything anyway. So, but yeah, that's the way you would handle it.
Going back, some of us looked at using these methods, sometimes called two-timing methods or multi-time scale analytical perturbation expansion. And those work okay as long as you have assumed some fixed steering law for the thruster. Did you ever look at these? And
No.
No one could see how to merge those with any variational methods to develop the optimal.
Oh, okay. No, I mean, I see. So, yeah. Does it really matter if you can't reconcile it with what an optimal control solution is doing, though? If it's giving you an answer that you like?
Well, we need an answer for example, fixed steering strategy or some sort of predetermined open loop, but it's not claimed to be an optimal strategy.
These aren't the same thing as like the Q-law type. Okay.
It takes into account analytically very nicely fast variables and slow variables.
Oh, okay.
You have to assume steering law.
Okay. I haven't heard of them, so yeah. I'd be lying if I said I did, but I'd like to learn more.
Probably just a comment. One of the things we've seen working with some of the owner operators is that using the electric thrust for east-west north-south station keeping is that they don't typically plan what their maneuvers are going to be. They get them from all the way up to wherever they tell them thrust in this direction at this time, et cetera, et cetera. And over a period of time, we've done some analysis and we started to find that they're not doing it the most efficient way. In some cases, they're actually going backwards from the direction they should be going in keeping track of the parameters. And so that might be an area of research too, is to look at optimality in that. I think the thinking with the electric thrust is that, hey, it's cheap, it's easy, it's free, we just do it all the time, and so who cares if it's optimal? And maybe part of that's true, but that's just some experience that we've seen. And kind of throw out as a comment.
Yeah, it's a good comment. So there's another one to, again, for people that are still deciding things, it's a good suggestion.
Marty, I don't know if you touched on this in your talk, but if anybody, I thought this was really interesting. You may or may not. Is when Marty kicks his code off, a lot of times it's a chemical trajectory guess. It kicks that medium fidelity code off, and then the optimizer takes, there's leveraging maneuver or something like that, and it just spreads it out. And so there's this connection where, as the thrust level goes up, sort of a classic chemical spirals, but for the interplanetary trajectories.
So what he's talking about is Chris has a lot of impulsive trajectory design, and we didn't do that in this case, but as an example, one way that you might design this low thrust trajectory before you knew what it looked like is to do a chemical trajectory search where you would find most likely that there's an optimal impulse right here, kind of collapsing this burn, another one right here. What you would then do is throw that into your Sims-Flanagan solver as an initial guess, and like Chris said, you almost always see this. It's smart enough to take the thrust and just spread it out into a low thrust burn. So that works really well for cases where that underlying structure exists in the problem. And yeah, there's a really, really nice connection there that can be exploited.
For that practice flyby in 1996 something, I don't know the letters, but anyway, excuse me. How close to the impact on, was it Digimon? Or
Digimoon.
How close is the flyby phase angle and the velocity compared to what you have? So how good of a practice?
Yeah, that's a good question.
It's always
think it's not as good as they wanted, but it was more or less the only game in town for flyby. I know it violates several constraints, but it at least allows them to, fire things up and train themselves under
go through the motions.
Yeah, go through the motions under a bad flyby. I can't remember how bad it violates things, but it's definitely, it doesn't satisfy them, and we can't make it satisfy them because you get what you get. Yeah, right. So it's not optimal from that sense. It's a little bit faster too. I think it's like 10 kilometers per second, and the terminal guidance is 6 kilometers per second on impact. So maybe that's a good thing. Maybe it's yeah, right.
As long as it's not crazy fast.
Yeah, right. Well, maybe it's a good thing that it's a more challenging case, than they actually have for the impact. All right. Thank you.
Good morning, everyone. Thank you for coming Saturday morning. My name is Mehrdad Mirzaei. I'm a PhD student of Dr. Singla. Today, I'm going to introduce a sparse collocation approach for finding feedback law in optimal control problem for spin stabilization for a spacecraft. I have worked this topic with Dr. Singla and with the help of Dr. Maji. Dr. Maji is an assistant professor in Texas A&M University. Actually, the spacecraft spin stabilization and attitude maneuvers has been done for a variety of reasons. Sometimes you need to pointing the antenna of the spacecraft to Earth or onboard experiments or guidance, or sometimes for cooling by sunlight or shadow, heating and cooling by shadow. One of the methods of spin stabilization is using the reaction wheels. Electrical motors that we are called the reaction wheels. As you can see in the picture, there is a 3 reaction wheels on each axis, X, Y, Z. If you want to rotate your spacecraft in one of these axis direction, you have to rotate the reaction wheel on that axis in the opposite direction. So then you will have your desired rotation. The background and motivation of this work is, first of all, the spin stabilization problem can be stated as an optimal control problem. You want to change the orientation of a spacecraft from one condition to another condition, and allowing this rotation, you want to minimize the cost function. There are two kinds of solutions for optimal control problem. You know that the open loop solution and closed loop solution. The open loop solution used to generate the optimal trajectories that minimize the cost function. There is a problem with this method. This method actually is not robust to changing in initial conditions or any disturbances. But we have a feedback control law or closed loop solution, which this solution overcomes the shortcoming of open loop solution. But actually, for finding the feedback law, you have to solve the Hamilton-Jacobi-Bellman equation, that is a multivariate PD equation, and solving this at JB equation is not at all easy. The solving of this equation rely on some numerical results. I have bring here two kind of methods: Galler-King method with series approximation, and the recently published method, series expansion method by Sharma and Baddeley. But actually, the difficulty exists in all of these methods is the course of dimensionality, because all of these strategies use the discretization, and so the main challenge is course of dimensionality and cost of computation. So let's derive the equation of motion. We have assumed a spacecraft with 4 reaction wheels. Here in the picture, you can see the body frame of the spacecraft. B1, B2, B3 are the axis of the body frame of the spacecraft, and we have 3 reaction wheels at each axis of the body frame, and another one, the fourth reaction wheel, is diagonal with respect to them. The angular velocity of these reaction wheels, cap omega 1, cap omega 2, 3, and 4. And the angular momentum of our system is sum of the angular momentum of the spacecraft and angular momentum of the reaction wheels. The angular momentum of the spacecraft is I omega. I is the inertia matrix of the spacecraft, and omega is our state variable that represent the angular velocity of the spacecraft. And the angular momentum of the reaction wheels is the term C transpose J omega. C is a matrix that indicate the direction of the reaction wheels with respect to the body frame of the spacecraft, and J is the inertia matrix of reaction wheels, and cap omega is the angular velocity of reaction wheels. You know that in the absence of external torques, the angular momentum will be conserved, and the time derivative of that will be 0. So, and here in this equation, the omega hat can be represented as here. You can see in the matrix. From this equation, I can find the equation of motion, and I will assume the term C transpose J cap omega dot as my control input. It's a kind of acceleration of reaction wheels. So now I can present my optimal control problem for this spin stabilization problem. In this problem, I want to minimize the cost function. My cost function is a quadratic cost function in fixed time that we already know this final time, subject to 2 kind of constraints. The first constraint is our equation of motion, and we will make this problem more complicated by adding the terminal constraint. You can see the psi is a terminal constraint, and in a domain of interest D. the objective of this problem is to finding the optimal control problem to minimize the cost function. And as I said, there's a two kind of solution for this problem. The first solution is open loop solution. By using Lagrange multiplier, nu and lambda, I will add my two constraints to the cost function, and the augmented cost function will be V bar here, and the corresponding Hamiltonian will be H. By taking a variation of augmented cost, I can find the necessary conditions of this optimal control problem. I will have two set of differential equations and two set of boundary condition and optimality condition. These two set of differential condition and these two boundary condition will form a 2-point boundary value problem. That by solving this 2-point boundary value problem, I can find the open loop solution. And as I said, this solution is sensitive to initial condition. So if you change the initial condition, or if you have a disturbance in your initial condition, you have to solve again this 2-point boundary value problem. In the closed loop solution, you have to solve the HJV equation. Here is the HJV equation, and we have two boundary condition for this equation. The first boundary condition is the value function should be 0 at the equilibrium point, that generally is 0, and the value function at the final time should be 0 and satisfy the terminal constraint. So it means that it should be 0 just on the terminal constraint manifold. Again, by using the Lagrange multiplier nu, I will add my terminal constraint to my boundary condition. And by minimum convergence principle, you can see that the optimal control is directly related to gradient of the value function. So if I can find the value function from the HJV equation, or at least the gradient of the value function from the HJV equation, then I'm done and I will have the optimal control. But actually there is a main challenge in this problem, and my main challenge is the value function just defined at the final time, just defined in the terminal manifold constraint. So the state space domain is being mapped to the domain of the terminal constraint. It's kind of shrinking the domain of the state space to domain of the terminal constraint. And you know that the changing the domain in any numerical solution is a big difficulty. Motivated by appearing the Lagrange multiplier in boundary condition for value function in previous slide, I will represent my value function function of both of the state variables and Lagrange multiplier. And then I will consider my value function as a multiplication of some unknown coefficients, Ci's, and some basis functions, Phi's, that these basis functions are a function of both of the state and Lagrange multiplier. The vector form of this value function can be C transpose phi. Before introducing my proposed methodology, I wanna introduce a collocation method that two of former PhD students in our research group has done with Dr. Singla. Michael Mercurio and other team has done this work and has published 2 papers in this work. One of the examples that they have done is the solving the HJV equation for infinite time. So assume that I know the value function at some points, that these points are collocation points, and I will approximate my value function as a multiplication of some unknown coefficients and some basis functions. Here, because there is no terminal constraint, I can consider just the value function is a function of state variables. So I can form this system of equations. Here, in the left side, I have the value function, noun value function at n points. then I have the basis functions at that point that it's known, and then I have a vector of the unknown coefficients. In this problem, there will be three conditions. Assume that the number of basis functions be less than collocation points, number of equations. Then I will have an overdetermined system, and there will be no solution for overdetermined system. Or the number of basis functions be equal to collocation points or number of equation, then it will be a square system and there will be a unique solution. It's really good. And if the number of basis functions be larger than the collocation points, I will have an underdetermined system and there will be infinitely many solutions for this problem. So choosing the basis functions and collocation points affects on the performance of this method. So choosing the collocation points and basis functions are related to each other. In one dimension, the most optimal choice is the choosing Gaussian quadrature points and using the Lagrange interpolation polynomial. If I have an n collocation point in one dimension, I will have an n-1 degree interpolation polynomial, Lagrange polynomial. But in multi-dimension systems, both of the Lagrange interpolation and collocation points require two tensor product. So you can see in the picture, in one dimension, I have 5 points. So the Lagrange interpolation will be in the degree of 4. But in 2 dimension, if I have 5 points at each direction, the order of the degree of my polynomial will be 8. Another choice is using the standard set of polynomial basis functions. Again, for choosing the quadrature points, I have exponential growth in multidimensional systems. If I have 7 points at each direction, I will, in 2 dimensions, I will have 49 quadrature points. And if I use the standard polynomial basis set, I will have a combinatorial growth. If these two be equal to each other, then I will have a square system and I will have a unique solution. But actually, in general, the number of the basis functions in this polynomial and number of the collocation points will not be equal, and it will be sometimes overdetermined or underdetermined. How can I guarantee that my system will be underdetermined? If I use the least number of collocation points, then I will have an underdetermined system. Yesterday, Dr. Singla introduced the conjugate uncentered transform or briefly cut methods to produce the least number of collocation points. As you can see in this picture, for example, for 5 dimensions, the Gaussian Legendre method will give you 3,000 points, but cut will give you just 300, 10 times less than Gaussian Legendre points. And it's just for 5 dimensions. And Paywood yesterday showed you that in 6 dimensions, Gaussian Legendre will give you 15,000 points, but cut will give you something like 700 points. And the beauty of this method is that this method keeps solution very accurate, and it will not reduce from the accuracy of the solution. Then I will go to finding the best selection of the basis function. How should I find the minimal degree of interpolation polynomials? In the literature, they have used the Vandermonde matrix and Gaussian elimination, partial pivoting method. But here I wanna propose a Sparse optimization for finding the least degree polynomial. and choosing the exact monomials that are suitable for our problem. Here, actually, we're using the optimization for the unknown coefficients, one norm optimization. Actually, ideally, we should use the zero norm optimization, but zero norm is not convex, and we can't do that. So the most close norm to the zero norm is one norm. So I will use the one norm optimization, subject to our constraint that they are the system of that linear equation that I have showed you. At each iteration, I will find the minimum or smallest coefficient, and I will set it as 0. Again, I will use another iteration, and the second iteration, I will choose again the smallest, and I will do this iteration till the number of unknown coefficients and the number of collocation points be equal, and then I will have a square system and unique solution. Here, I will show you example, simple example. I have a noun polynomial, px. I will choose 4 points, legendre points in each direction. So I will have totally 16 points, 16 collocation points in 2 dimensions. And I will choose all the polynomials up to degree 6. So I will have 28 basis functions, or in other words, 28 unknown. And I will have actually 12 basis functions more than my collocation points. So I should eliminate these coefficients. And I will find the value. Then I will find the value function at these 16 points because I know the polynomial. And then form the underdetermined system, linear system of equation, and I will compare it with least degree interpolation in next slide. Here in the left side, you can see that the approximation of these polynomial with respect to the original polynomial will have an error something like 100. But in the right-hand side, you see the sparse optimization with comparing with original polynomial, and the error will be something like in order to 10 to the power minus 8. And the beauty of this example is exactly this sparse optimization produced the exactly that monomials that was in the original polynomial. 16 quadrature points. Now I want to go to my own problem. I will use the open loop solution to help me to find the feedback law. There is, you know that the co-state in the open loop solution is actually the sensitivity of value function with respect to states or gradient of the value function. So if I solve the open loop solution for n initial condition, that I will use the cut method for producing this n initial condition, then I will have the trajectory at all of these n points, the optimal trajectories for co-states, for states, and Lagrange multiplier. From the open loop solution, I will find that the Lagrange multiplier is constant along the optimal trajectory, and it's the function of initial value of the state. By substituting my approximated value function in co-state matching condition, I will have this set of equation. The difference of this problem with the problem that I showed you is that here, because it's a finite time HJB, actually the coefficients are changing during the time. So I have to solve this system of equation at each time step. And if my system be in d dimension, so at each dimension I will have n equation. So I will form this system of equation. I will have n times d equation, and I will have m unknown coefficients, and the matrix A shows the gradient of basis function with respect to states, and C is the unknown, and B is the value of the co-states at each time step at each of these endpoints. So for solving this system of equation, I will use the again sparse optimization. Here I will use a weighting function, and I will update this weighting function at each iteration. At the first, I can choose my weighting function as identity matrix, and then I will update my weighting function like this. That for example, for each coefficient, the weight of this coefficient will be the 1 over the this coefficient in last iteration plus some epsilon. So if in the last iteration this coefficient was very large, so the weighting function in the next iteration will be very small. So and if the value of this coefficient in the previous iteration was small, the weighting function will be very large in the next iteration, and actually the optimizer try to minimize, try to make these coefficients 0. And this is the algorithm that I have used for finding the best basis functions and using for making unknown coefficients to 0. For the numerical results, I have used this matrix as my inertia matrix, and J is my inertia matrix for reaction waves. I have used for R and Q identity matrix, and my Q weighting matrix is equal to inertia matrix. My domain of interest is -5 to 5 degrees per second for angular velocity of the spacecraft, and I have solved this problem for 20 seconds. And my terminal constraint is all of the states be 0 at the final time. For the open loop solution, I have used the MATLAB built-in function BVP4C. That it's a function that solves the 2-point boundary value problem for you. And then by my proposed methodology, I have find the cost function. The first 2 rows, cut1 and cut2, show two of those collocation points. The cost function from open loop and closed loop are exactly the same for these 2 points. And then I have used 5 random initial conditions, and you can see the difference between the cost in open loop and the closed loop solution is in order of 10 to the power minus 4. For example, in the first random initial condition, the cost value at the open loop is 4.1755, and in the closed loop is 4.1752. Then here I have my unknown coefficients that I have calculated by first one norm optimization. You can see at the given time, on average, we have only 174 coefficients that they are not 0, they are non-zero, out of 8,008 unknown. Because at the first I have used all of the polynomial up to degree 10 as my dictionary polynomial, and it has a 8008 monomials. And you can see the coefficients of the quadratic terms like omega1 nu1, omega2 nu2, and omega3 nu3 dominate other non-zero coefficients. Other non-zero coefficients are almost zero, but these three has a large value. And we can conclude that linear controller is a good approximation for the nonlinear problem. Next, I have compared the trajectory for three random equations for open loop and closed loop solution. You can see they are matched exactly, but actually there is a small error between the state trajectory and control trajectory for these three initial condition. The order of the error for state are 10 to the power minus 5, and for controller is 10 to the power minus 4. Thank you so much. Have any
No, this is a good question or not. Theoretically, is the closed loop controller, because of the approximation, that would you expect that to have inferior results in the open loop overall?
So can you repeat the question?
Sure, sure. Theoretically, between the closed loop and open loop controls, did you get what you expected? For instance, would you expect that the open loop control would always have superior results to the closed loop controller?
Open loop solution has a exact solution, has exact answer, but actually it's just for one initial condition. If you change your initial condition, you have to solve your this open loop solution again as another 2-point boundary value problem. If you have the feedback or closed loop solution, there's no need to solve your problem again. You have a law and you just need the current value of the states.
Yeah, I guess what I was getting at is, if I sat down and I wanted to solve this problem, in general, would I expect the results to be as close as undergrad? Because your results were really spot on against each other. I was wondering that as a general result or specific.
It's like to help him out because he's solving the HB equation. Okay. So in the HB equation, now the initial condition does not matter because you have solved over the whole domain. You give the initial condition and it is going to give you the optimal solution. What he's doing in the end is he's just checking it because it's a collocation approach. At a collocation point in the initial condition domain, yes, for the collocation point, you have exactly solved the HB equation, but you are not guaranteed at any other point. So he's just taking some random point in the initial condition space, solving the open loop and trying to test it out. How good was the collocation? And in this case, the collocation came out to be very good. Okay. The beauty of this is solving the HB equation, it is getting converted into convex optimization. Okay. And you are not parameterizing, even though you are parameterizing the value function, the method is you can call it a parameterization free because this basis function can be anything and optimization will pick which basis function should participate. Okay. So coming to even in the some of our problem like the impulse or the switching thing, you can actually have all of those parameterizations. You can make your dictionary to be as large as you can. And then this sparse optimization will go and try to pick the correct parameterization which should be appropriate for the given problem. And then the closed loop is because you're solving a HB equation with a guarantee of V0 to V0, you are also getting a stable control. Stable feedback control, right? More than asymptotic stability, because you are saying that within the finite time you are achieving your equilibrium point.
Your question was in general, do you expect the result to match that well?
Yes, theoretically, you cannot give a guarantee for any arbitrary, but what we have seen is we have solved like the conventional spin stabilization in the infinite time problem where you have actually an analytical solution of HJB. We have seen that this actually methodology go and pick up the exact solution, okay, the analytical one. So we have like 3, 4 or 5 benchmark problem which my former student have done, and all the time it go and nail down the analytical solution. Even in the Hohmann transfer, like going from the circular orbit to the other one, all the time it go and pick up the analytical solution.
How are we on time?
We're a little behind.
Okay.
You're fine.
All right, all right.
You can do the full high five.
I'll start when everybody's ready. I'll let you take a breath. Okay. So let me sort of take a step back and tell you about the slides I'm going to present. I adapted this presentation from a slide package that we built to present to the subsystem engineers to sort of demystify the Europa Clipper trajectory, because when you look at it, it looks really complicated, and and if you're an RF engineer somewhere, you don't necessarily know how to deconstruct it to understand it. So I found that these slides were useful for that, but then I also tried to drop in some flavors of what Marty sort of did, is, identify methods that we use in case you ever want to try to build stuff like this. I think you have enough engineers here to probably build trajectories like this if you really wanted to.
Hey, Chris, why are the ER and A capped and the others aren't?
I don't know. I think they thought it looked cool.
No. There's a cool logo. Open it on Mac, but the font doesn't transition to Windows.
It's a logo kind of deal?
Yeah, but it only opens correctly on Mac. So when you open this up,
yeah, they're all Mac users.
But when you open it up on Mac, it has this really cool font.
Yeah, that's a shame. Yeah. Yeah. Okay, so I'll give the team credit. So Marty and I work on this at the Applied Physics Lab, but there's a much larger team. This mission actually is the mission design and navigation split between East and West Coast. So Applied Physics Lab has a piece of the design, JPL has a piece of the design, and we, as much as practically possible, we work as a single team. So how big is a team like this? For the people. I think this is interesting just to see, how many people does it take to design a mission like this and fly it. We're going into phase C next year. We're in phase B right now. But you can see Marty and I are listed under the trajectory design team. It's led by JPL engineer Brent Buffington. And some of these names you might recognize, just going through the literature.
Just flight dynamics. This is the
Right.
whole mission.
Yeah.
Just the flight dynamics.
Right. This is just the flight dynamics.
Oh, that's the left. That's the
Yeah.
logo down there on the left. That's
Yeah,
what
there's
it's
the
supposed
cool.
to be.
There's the cool in case you're interested. Kind of looks sci-fi or something. Okay, so that doesn't look as good. Oh well. Scientists really have some great slides on the mission motivation and what we're trying to do. I'm not going to do it justice, but I'll say this: Europa is a really cool place to visit because it has water and it has energy. So it has actually more water than Earth does, they think, and it gets energy from the tidal fluxing of the ice shell, and it causes what they think are things like geothermal events underneath it. So we're hoping there's going to be some like fish or space whales, but we'll see. Maybe just the equivalent of sea monkeys. But this mission used to be in orbit. It's a flyby mission now, and it's about 10 years ago it was initially an orbiter, and you may know this, that there's a really harsh radiation environment. As you get to Ganymede and move inward into the system, the radiation belts around Jupiter are really nasty, and it causes a lot of problems for spacecraft designs because it causes expense. Everything has to be radiation hardened, so on and so forth. And so they said, NASA said, the mission's too expensive, find another way to do it. So they came up with this flyby concept, and so that's where you get this trajectory that looks like, you know, you probably are too young to remember spirographs. I still have those with kids. I feel old now. I had one. Anyway,
I just wanted for my
right.
kids.
So it looks like you took a spirograph and made that trajectory, but what it's doing, it has a specific purpose. It's just really, they call it dipping their toe into the radiation belts, flying by Europa, and coming back out. And the whole goal is to, and these are ground tracks on Europa, the goal is to get global coverage of the moon. So you sort of have this happy medium. You're still looking mostly at the entire moon surface, but you're just dipping your toe in. I don't think you can ever completely mimic what an orbiter can do, but it gives you that nice happy medium. And it's a really cool mission to work on as a trajectory designer because there's a ton of trades